Hi, I am Liu Mingmou from Nanjing University.
The talk is about lower bound for succinct range minimum query. This is a joint work with Yuhua Chen from Princeton University. Range minimum query, aka RMQ, is a classical data structure problem. Given an array of numbers, the queries may give some ranges and ask the minima over the ranges. For example, the minimum between the third element and the eighth element in this array is 1. However, in this work, we study a variant of RMQ, which asks for the index of minimum. In this case, the answer for query RMQ of 3 and 8 is 4 rather than 1. The RMQ is a fundamental problem, which has numerous applications in computer science, including text processing, graph problems, and bioinformatics. In particular, RMQ is a critical component in aid of the application of the longest common prefix array in suffix array. RMQ is equivalent with the lowest common ancestor problem for binary trees. The equivalence is established via a structure named Cartesian tree. Cartesian tree is introduced by Viola'10 in 1980. Given an array of numbers, the Cartesian tree with respect to the array can be constructed recursively as follows. At first, we take the minimum over the whole array as a root. Then, the array is broken into two subarrays by the root. We construct Cartesian trees with respect to the two subarrays recursively, and let them be the left and the right subtrees of the root, respectively. With Cartesian tree, the RMQ can be reduced to the lowest common ancestor problem in the tree. For example, the lowest common ancestor of 12 and 20 is 10, which is a minimum of range from 6th element to 8th element. It is easy to see that one cannot compare 3 and 5 in this array with range minimum queries, since there is 1 in between. Similarly, we can compare any pair of elements which are separated by 1. It is also not hard to see that, given all the answers of range minimum queries, we can construct a unique Cartesian tree, and given any Cartesian tree, we can construct all the answers of range minimum queries. By this observation, one may conclude that the input is in fact a binary tree. RMQ has a classical textbook solution, which uses ON space and constant time. As we argued before, the input is in fact a binary tree, and the size of input universe is the Catalan number. The logarithm of nth Catalan number is 2n minus O log n. Therefore, the truly linear space should be On bits and using On over log n words if the word size is log n. Consequently, we choose the uniform distribution over all n-node binary trees as the hard distribution to prove the lower bound. It is because the setting maximizes the input entropy and matches the space benchmark. In 2007, Sadakane presented the first linear space data structure for RMQ. Later, Fisher and Huon presented the first succinct data structure for RMQ. A data structure is called succinct data structure if the space usage is close to the minimum space usage to store the database. The extra space usage is called redundancy. 3 years later, Navarro and Sadakane improved the space upper bound to 2n plus n over polylog n bits. Naturally, two questions come to our mind. First, is there a lower bound for RMQ? Second, does the state-of-the-art data structure with constant time have an optimal space upper bound? In this work, we presented the first lower bound for RMQ. Our lower bound shows that the state-of-the-art algorithm is optimal in the regime of constant time. Before introducing our approach to proving lower bound for RMQ, I would like to introduce the computational model. The CRPRO model is introduced by Andrew Yao in 1981. It is very similar to the famous RAM model. In a CRPRO model, operations are free, except memory access. In a CRPRO model, a data structure is interpreted as a table of memory cells. The interaction with data structure is modeled as a procedure of CRPROving. Given a query X, the CPU chooses a memory cell C1 with its unlimited computational power in the first round. The CPU retrieves the content of C1 by CRPROving. With the content of C1 and query X, the CPU chooses a new memory cell C2 in the second round. The procedure keeps going on and on. After T rounds, the CPU has collected enough information and comes up with its output with all the known information. Now let's move to our proof sketch. In fact, we prove a lower bound for a problem named pretty Z. We believe pretty Z characterizes the hardness of RMQ. At first, we reduce pretty Z to RMQ. Then, we show lower bound for pretty Z. In order to do this, our strategy is a new variant of round-elimination in carefully chosen hard queries. We use a series of new ideas and proofs to show the round-elimination is feasible. The classic round-elimination is developed by Pătraşcu and Viola in 2010. Their proof uses a variant of round-elimination in a tweaked CRPRO model. In this model, a data structure may use H bits of space and extra P published bits. The published bits may actually depend on the database. It also can be accessed by CPU for free. Pătraşcu and Viola argue that for data structure using P published bits and T time, we can publish P times polylog M cells to save one time of memory access for many queries. By recursively applying this argument, we obtain a data structure that uses some published bits but doesn't access any memory cell. So the number of published bits in the final data structure can't be less than the information theoretic lower bound. The key argument lies in publishing more bits and saving memory access. It is feasible, since the answers of queries are correlated. We evenly choose a set of queries Q1. Then, if most of queries don't probe the cells probed by Q1, with good probability, we show two consequences. Firstly, a random set of Q2 doesn't probe the cells probed by Q1. Secondly, lots of information is both contained in the answers of Q1 and Q2. The information is both contained in the cells probed by Q1, Q2 as well, since CPU can recover the answers of Q1, Q2 with the cells. However, Q2 don't probe the cells probed by Q1, which means the bits are wasted. So, we can remove 5p bits by compressing from the data structure. In the end, we have a too good to be true representation of the database. Unfortunately, the Q2 argument doesn't work for RMQ. Why is that? Because the argument works for average case lower bound, but we believe that RMQ has efficient average case solution. Hence, we move our concern to a set of hard queries, which are correlated with the database, and we apply round elimination on the hard queries only. Since the hard queries are highly correlated with database, We cannot use some cells probed by some specified hard queries to compress the cells probed by Q1. It is too expensive to write down hard queries. In order to get over this, we develop a more powerful lemma. We show that for the properly choosing QPub, the cells that are not probed by QPub contain lots of information about the answers of QPub. All the three steps are non-trivial for PretZ. We will elaborate them later. First of all, we introduce the PretZ problem. Note that we are dealing with succinct data structures, so we have to control the increment of space usage in reducing carefully. The starting point is very simple. We observe that the RMQ becomes predecessor search if one end of the query range is fixed. For example, if the left ends of the queries are fixed to 1, this problem becomes predecessor search with database 1, 4, 6, and 9. In particular, the answer of any query with right end that is less than 4 will be 1. So, it suffices to prove lower bound for the underlying predecessor search. However, an obstacle emerges immediately. The underlying predecessor search has very low entropy under our reduction and distribution. A simple reduction introduces unacceptably large redundancy, which rules out any non-trivial lower bound. Our patch is simple. We force the algorithms to waste space on dummy information, which is the Z. Formally speaking, the database of PretZ consists of D subproblems and a large integer Z. Each of the subproblems is a set of U distinct elements from a universe of size B. PretZ requires the data structures to answer two kinds of queries. Execute predecessor search in some subproblem, or return the Z. We care about the time-space trade-off between the time cost on predecessor search and space cost in total. Note that the time complexity on query Z can be arbitrarily large. We then embed the database of PretZ into Cartesian tree to reduce it to RMQ. We get the subproblems into pairs. A pair of subproblems is embedded into a small tree which has 2B plus 3 nodes. The 2U data points in the subproblems are embedded into these two paths, and the other elements from the universe are embedded into the subtrees. To answer the predecessor search in subproblem I, we just return the lowest common ancestor of the dummy node corresponding to the subproblem I, and the node corresponding to element X in subproblem I. Recall that database for RMQ is one single binary tree, so we merge the D over 2 small trees into one. Note that the lowest common ancestor oracle still solves the predecessor search, since the merge doesn't change the in-order traversal. Then, we let Z encode the remaining information of the tree. That is the way we merge the D over 2 small trees, together with the structures of the subtrees. To answer the query Z, we just retrieve the whole tree and compute the Z. Query Z forces the data structure to waste space on the Z. The trick overcomes the previously mentioned obstacle. By properly choosing the parameters, we show that if there is a data structure for RMQ using R bits of redundancy and T time, then there is a data structure for PretZ using O R log n bits of redundancy and T time. We prove the lower bound for PretZ. By our settings, The lower bound for pre-Z implies the desired lower bound for RMQ. So it suffices to choose this lower bound for pre-Z. We choose the lower bound between the cells probed by hard queries, and QPUB should be large. By recursively applying the round-elimination lemma, we obtain a too-good-to-be-true representation, which implies a lower bound for pre-Z. By R reduction, we obtain the desired lower bound for RMQ. We elaborate the three steps for proving round-elimination lemma in the following slides. Picking a good set of queries is not an easy task under our distribution. If we pick too many queries, we will publish too many bits in each round. In that scenario, we cannot eliminate many rounds. In the end, we cannot prove a good lower bound. We pay extra p-log(n) bits to specify the QPUB. It is okay, since what we save is more than what we pay. We break the DSA problems into p blocks. Every block has m data points. What we want are the blocks of length m squared. Finally, we pick queries evenly in the good blocks. It can be checked that many blocks are good, and the answers of QPUB reveal lots of information in good blocks. Here we choose E to measure the revealed information. By putting everything together, we conclude that we have picked a good set of queries. We choose the queries on all input data points as the hard queries. It turns out that giving arbitrarily 1 minus epsilon fraction of data points, we can fully recover the E with a short auxiliary bit string. We are not going to elaborate the highly non-trivial proof in this talk. You can find the details in the paper. Finally, the last step. Recall our compression procedure. After the first step, we write down all the cells which are not probed by QPUB. To make it happen, we have to know the addresses of the cells probed by QPUB. We cannot just write the addresses down, because the query algorithm is fully adaptive. In other words, the addresses may reveal lots of information about the database. One may easily bypass this difficulty by assuming the query algorithm is non-adaptive. That is to say, the set of probed cells depends on the query only. The solution is inspired by one simple observation. The address of the cell probed in else round is fixed as long as all the L-1 previous cells are fixed. Then, we can choose a good L such that the set of cells probed in else round reveals lots of information about the answers of QPUB. In this way, we achieve some kind of non-adaptivity. We choose the good L by the chain rule of mutual information. Now, we are ready to show the compression procedure. At the first step, we write down everything except the cells probed in else round by QPUB. In order to do so, we write down the p-published bits and write down some bits to inform QPUB. Then, write down the cells probed in the first L-1 rounds by QPUB, followed by the contents of the rest cells, except the cells we want to compress. In the second step, we write down auxiliary bits to recover E. Finally, we compress the cells probed by QPUB in else round, given E. We assume the new Published bits save at most delta probes in expectation. By putting everything together, we conclude that the delta has to be large to avoid contradiction. In conclusion, we prove the first lower bound for RMQ. Our lower bound shows that the state-of-the-art algorithm is optimal in the regime of constant time. The lower bound is proven by reducing from pre-Z. We employ a new idea to save the space loss in reducing for proving lower bound. We find new ways of proving worst-case lower bound and attacking fully adaptivity to prove lower bound for pre-Z. There are some interesting open problems. Can we close the gap between lower bound and upper bound for RMQ in general case? Is there a more powerful tool to deal with the adaptivity? That's all. Thanks for listening. If you have any concern, please shoot me an email.